All right. Good morning, everyone. So we'll kick off today with Siva Balakrishnan. Siva is a professor at CMU. He's worked on a union of topics in causality, statistics, and optimization. He's done a lot of exciting work, like in kind of versions of robustness, distribution shift, and questions around statistical limits of causality. And he's going to tell us some about that today. So let's take it away.
Okay. Thank you all for coming. Thank you to all the organizers for inviting me. It's a pleasure to be here. I'll be here for the whole year, so please come talk to me. Okay, so today I'll be telling you some things. A lot of it will be background and things. Some of it will be newish work. Everything will be joined with Edward, who taught me everything I know about causal inference. It'll also be joined with various subsets of the rest of them. I might be bad about giving references at various points, but Jamie Robbins is the originator of a large fraction of everything I talk about. So if you want historical references, just go read Jamie's early works, and hopefully that. But again, if you have questions, just stop me, and I will give you more references at various points. Okay, so let me begin with one slide of very broad motivation. So causal inference, that is, I'll tell you a little bit more about what exactly it is, but it is one of the fastest growing subfields of statistics and machine learning, partly because causal questions are at the heart of many different applied fields, including epidemiology, public policy, econometrics, and so on. There are lots of advances that happen across all of these fields on the methodological front, and this means people come up frequently with new causal quantities that they'd like to estimate. They design new ways to estimate them, and so on. A lot of this work very fruitfully exploits a certain interface between machine learning and causal inference, and I'll tell you what that interface is at some point. But that's part of why there's a lot of activity, is because advances in machine learning somehow have some nice implications for advances in causal inference. On the other hand, maybe I'd try to convince you that the theoretical foundations or the statistical foundations somehow lag far behind. For various causal quantities, we have very little understanding of what the fundamental limits are. Like, have we reached them? Are these estimators that people design frequently, are they good? Are they bad? All of these questions are largely open. Okay, so before I tell you anything about causal inference, let me tell you a little bit about a different problem, which is more classical in statistics, called functional estimation. So here's the setting. You observe a set of samples from some distribution P. And what you'd like to do is estimate something. It's called a functional. So you should think of a functional as a single number that somehow summarizes the distribution. So it's a single number associated with the distribution. Throughout, we'll be thinking of what are called integral functionals. So you should think in your head of something like the integral of the square of the density, or something like the negative entropy, any of these things. So you should think of them as single numbers associated with this distribution. And a very classical question, it goes back to Charles Stein in the 1950s, is estimating a functional as hard as estimating the distribution? So is it as hard as estimating a potentially complicated non-parametric object? Or is it as easy as estimating a single number? So should I expect 1 over n rates, which is the rate I would expect if I was just estimating a single univariate parameter? Or is it as hard as estimating the whole distribution? Or is it somewhere in between? And if it's in between, where is it? Everyone okay so far? Let me just remind you, just feel free to interrupt me if you have any questions. Yeah.
What are you given as input here?
You're given samples from the distribution.
And then can you evaluate P on the samples?
No, you cannot. You're just given samples from the distribution, and the functional is, say, the entropy of the distribution. So given samples, tell me what the entropy of the distribution is. Thank you. Yeah.
You're somehow thinking of functions of P, not of the random variable, like not of X.
Correct. Okay. Good. Okay. So why might one care about this? Well, there are many applications, but maybe two of my favorites are when you think about things like hypothesis testing. It's very naturally phrased as a functional estimation problem. So hypothesis testing would be, I give you some samples from a distribution, and maybe I want you to distinguish two cases. Is the distribution uniform, or somehow in some distance far away from uniform? And a natural way to try to design tests that distinguish these two would be to construct functional estimates that estimate this distance and then reject the null whenever your estimate of the distance is large. So it has some intrinsic connection to hypothesis testing. The other is, it comes up often in machine learning, which is I give you samples from pairs of distributions. So I give you a bunch of samples from P and a bunch of samples from Q, and I ask you to estimate some notion of divergence. These are also functionals. They're single parameters that somehow summarize the two distributions that I'm giving you. So I could ask you, given samples from two distributions, tell me what the total variation between them is. And again, you are back to this question that, is estimating, say, the total variation between two distributions as hard as estimating the distributions themselves, or is it somehow much easier? Okay. These problems arise everywhere in statistics, in theoretical computer science, in information theory, and so on. And I'll tell you about connections to all of these fields at some point. Okay. The other very before we get there, so maybe the first naive thing to try, if I gave you a functional and said estimate, say, the entropy, the first natural thing to try is called a plug-in estimator. So what is it that you do? You take your distribution, you construct your favorite density estimate. Say, if it's a continuous distribution, you do some kernel smoothing, something like that. And then you compute the entropy, say, of the kernel smooth estimate. So that is, to compute an estimate of the functional, you estimate the distribution, plug it in. So that's why it's called a plug-in estimator. And you estimate the, say, entropy of the estimated distribution. And intuitively, you can see this fairly quickly. If your functional is nice, so by nice, I mean sort of behaves Lipschitzly in your estimate, then you might imagine that this will obtain some rate of convergence. Roughly, you can argue maybe in some cases that if your functional is nice, then the plug-in estimator will inherit what are called first-order rates. That means it'll be roughly as accurate as your estimate of the density. Okay, so the maybe first question that one should ask is this the best thing that one can do? And if it's not, why is it not the best thing that one can do? Yeah.
Sorry for keeping that up.
Please.
Are you assuming that P has like some smoothness property?
Yeah,
that if it's a discrete distribution, you're not going to be able to do this, are you?
Not sure why not.
Well, because if it's a discrete distribution of size n on n different points, then until you sample square root of n points, you're not going to really be able to tell what n is.
Sure. I will talk about both the continuous and the discrete case. And you should think about it as, yes, I'm OK with sampling square root of n things. I'm OK with sampling even more than that. But the question is, how many do I need to sample? But yes, I will tell you about both versions of this problem. But for now, maybe you should think about it as it's a continuous distribution and has some smoothness properties. OK, other questions? OK, so what is the intuitive problem? The intuitive problem with trying to construct plug-in estimators is that of bias. And the way you should think about this is, suppose I was trying to estimate something like the integral of p squared. That's a canonical nonlinear functional. Then even if I gave you somehow a magical density estimate that was unbiased for p, once you square it, it's no longer unbiased for p squared. So p hat squared is not particularly a good estimator of p squared. And maybe you're better off trying to design an estimator of p squared and then plugging it into something. Right? So the issue with plug-in estimators is that they can often have unnecessary amounts of bias, at least if you're not careful in how you do it. Everyone OK with this?
So that's an issue that's independent of this being loose or something, right? That's not the same statement. Okay. Then this bound is also wrong for other reasons than bias. I mean, it's also conservative.
Sure. The bound is just a high-level guideline of what you might expect. It's not necessarily tight in, yeah. OK? Very good. OK, and maybe I'll say this again, and I'll say this many times again later. So functional estimation problems, they're a very interesting interface between statistics, TCS, information theory. Lots of people have thought about these types of problems. In TCS, they sometimes go by the name of sublinear algorithms or polynomial methods, and we'll come back to why they have these names. But is everyone OK so far? Great. So even if you didn't want to estimate things like entropy, there's another very good reason why you should care about functional estimation. They come up a lot in causal inference. And so let me tell you why they come up in causal inference by explaining what the most basic problem is that one can think about in causal inference. So here's the setting. I want to estimate the effect, the causal effect of some binary treatment on some outcome y. So you should think of the binary treatment as I administer you a drug or not. And I want to know what's the effect that this treatment has on the outcome y. And so on some outcome, say whether you have headaches or not. And the first question is, how do you formulate this? One way of formulating this question comes from what's called the Neyman-Rubin causal model. So the way that we think about this is that there are two potential outcomes. So every individual here has associated with them two potential outcomes. One of them is what would happen if they took the pill, the drug, and the other is what would happen if they don't take the drug. Right? So this is these two potential outcomes that you could observe. And what makes causal inference hard is that I can either choose to give you the drug or not, and you will see only one of these two potential outcomes, and causal quantities are inevitably some contrast between the two potential outcomes. Okay, so you should imagine the most favorable setting is I run a randomized control trial, I randomly assign half of you to take the drug. So for all of you, I will see one of your potential outcomes, and then the other half, I don't give you the drug, and I'll see the other potential outcome. But for any given unit, I don't see both of these outcomes. Everyone okay so far? So what is it that I want to estimate? Maybe the canonical first thing that one might try to estimate is called the average treatment effect. The average treatment effect is just the expected value of this contrast between two potential outcomes. Again, you don't see both of the potential outcomes. You see only one of these two. But I'd like to estimate this difference. And this is what I said. So sometimes the outcome that you see is called the factual outcome, and the one that you don't see is called the counterfactual outcome. Okay, so maybe, again, all of you have seen this before, but I'll go through it quickly. The most well-known, oldest way to infer things like, estimate things like the average treatment effect comes from an idea of randomization. So randomization is what I just described to you. I randomly assign half of you to take the treatment and half of you to not. In this case, inferring causes or estimating the average treatment effect is somewhat easy because the randomization ensures that the two potential outcomes are independent of the assignment. I'm randomly tossing a coin and deciding who to assign treatment to and not. And then you can easily check that an unbiased estimate for the average treatment effect is I take an average amongst the people who got the treatment. That's an estimate of the expected value of y1, which is the first potential outcome. And I can subtract off. So I just take the average amongst the treated group of the outcome and then subtract off the average amongst the non-treated group. Everyone good so far? Okay, great. So what's the problem with this? It's that often it is not ethical or costly to run randomized control trials. So what people instead want to do is try to infer things like the average treatment effect from observational data. So what I have is just data that measures, say, the treatment and the outcome. It wasn't assigned by me, but I'd still like to estimate things like the average treatment effect. So this is called the observational setting. And maybe the first problem, again, even if you haven't heard of large language models, you've almost certainly heard of confounding. And confounding is just this problem that if I don't randomly assign treatment, then the groups that take the treatment and not are not necessarily comparable. So the picture is supposed to be saying, suppose I want to know if sleeping with your shoes on gives you a headache in the morning, then I might go out and ask a bunch of people, did you sleep with your shoes on, and ask them if they had a headache the next morning. And this would be, I can't use that data directly to figure out whether this causal effect exists or not, and partly because there are a bunch of people who maybe there are common causes for these two things, which is maybe drinking gives you a headache and causes you to sleep with your shoes on. And just intuitively, the groups that take treatment and don't are not necessarily comparable anymore. Everyone okay so far? Okay, great. So this is just inward saying that the expected value of the potential outcome, which is what I want, is not necessarily the same as the expected value of the potential outcome in the group that takes the treatment. How do we make progress? Well, one way of trying to make progress, do you have a question? Oh, sorry. One way of trying to make progress is to try to correct for the confounders. So if you knew what they were, or if you knew what the most important ones are, you might try to say, okay, I can't compare groups which have different values of the confounders, but maybe I can go and measure them and try to only somehow compare people who have the same value of the confounder. Okay, and this will lead you quickly to one of the most basic ways of estimating causal effects, which is you try to now measure a bunch of potential confounders. They will be called X. Then you have your treatments and you have your outcomes. And now you are going to make this assumption. As long as this assumption is plausible, the rest of the thing that we're about to do will make sense. What is the assumption saying? It's saying, as long as I control for all of these confounders, I only compare people who have the same value of this X quantity, then I still have this independence assumption being true. Right? So now, rather than make the assumption that the treatment is independent of the potential outcomes, which is maybe not so plausible in an observational setting, you say, OK, once I adjust for these confounders, that assumption is in fact true. Is everyone OK so far?
What are the confounders? That would be what's the potential?
Yeah, so there's some trade-off. You ideally, maybe correcting for lots of things will also be kind of expensive statistically. So maybe you want to figure out what are the dominant things. This is like a domain knowledge question. So that is, in the example I gave you, maybe you can try to say, OK, what are things that might cause you to sleep with your shoes on and whatever. Things that could potentially affect both treatment and outcome, and you go and measure those. But you at some point have to tell a story that says, OK, I've somehow controlled for the most important, most obvious confounders, at least.
Is this somehow like the counterpart of backdoor criterion, I guess, if you're in the kind of graph view?
Correct. Yeah, exactly. This is the backdoor criterion. I mean, the next step will be maybe called the backdoor criterion. So this is maybe what Andre was saying, that, OK, once you make this assumption, if you think about a graphical model, then you can see that you can rewrite something like the average treatment effect. Now, under this assumption, you can rewrite the average treatment effect as the expected value of the difference between two regression functions. So these two regression functions are, I try to say, what is the average of the outcome amongst the treated units, but I look at it conditional on X, and then I subtract it off, and then I take an average on the outside over the X's. OK, so this is saying first adjust for X. Now it looks like a randomized control trial. You subtract off your potential outcomes, and then you average over the X's outside. OK, so this is just saying, and if you haven't seen this before, I'll work it out for you. So this is just a standard thing, which is just how do I identify the ATE under the assumption of no unmeasured confounding. So this conditional independence assumption is called the assumption of no unmeasured confounding. So this is what we want. You want to estimate the average treatment effect. You can imagine first conditioning on X, and then taking by the law of total expectation, I can write it this way. And then now I will use my conditional independence assumption, and it will say that once I've conditioned on X, I can throw in an additional thing that depends on A because of the conditional independence. That's OK. It's the same thing. And crucially, now I'm subtracting off. There are still potential outcomes here, but it's the observed potential outcome. So in this group where A is 1, I'm using some fact about Y1. And in this group where A is 0, I'm using something about Y0. So these can be rewritten in terms of the observed outcome. So this, in turn, is simply this difference. And then you have to throw an outer expectation out. Yeah.
So this assumes that at least the people were randomly drawn, right?
Correct.
So it doesn't like in observational data you can have two things. Like one is that the treatment was not randomly given, but it could also be that the people who chose to answer a survey in the first place might not be IIT samples from the population.
Yeah, so that would be called something else. Yeah, so that would be called transportability or something. You can say, even if I ran a randomized control trial, I might run it on you people, but maybe I actually want to know what the causal effect is on some other people, and then I have to make some assumption. But yeah.
I'm a bit confused where the expectation on X disappeared, because
Yeah, there is an expectation on X in the last line. Is that what you're asking?
where is it? In the top, the tau in the top is a deterministic quantity. There's an expectation over X there, but
yeah,
the other
everything else.
Random quantities depend on X.
Yeah, so each of these, there are typos. You should just have an expectation over X on the outside of everything. So the formula I wrote you here is the correct one, which is you take the difference of regression function, then take an expectation on the outside. Thank you. OK. Good.
Wait. Okay, so I'm just confused. But
Yeah.
then, if I take expectation over X, then the outside, why doesn't this? I mean, I can. I mean, I'm just trying to figure out why I can't just like say that this is equal to like take the law of total probability now and get rid of the x there.
So you're somehow you should not be weighting every strata equally, right? Like you'll see it again in a different form, but the regression is somehow doing something for you here, right? Like it's estimating a conditional expectation. You can't do what you just said. You will see it again, but okay, great. So this suggests a very natural estimator once you stare at this formula, which is called the plug-in estimator. So importantly, and to connect back to the earlier part and to the later part, you should think of this as a functional. This is now saying, I'm giving you samples from a distribution. There's all these things in that distribution. There's this regression function, another regression function. I don't care about any of those things. What I care about is this one number, which is the average of the difference between these two regression functions. So this is a functional. It's a single number associated with this distribution. All these regression functions are just nuisances that I don't care about. But once you stare at this formula, you will come up with what's called the plug-in estimator. It just says, solve these two regression problems, estimate these two regression functions, take the difference, and average it over your population. This is the one plug-in estimator of the average treatment effect. Everyone okay so far? Okay, said that already. You can also think about this as some sort of basic domain adaptation problem. So suppose you think about first just focus on estimating the expected value of y1. This is just what would happen if everyone in the population got treatment. What would the average outcome be? You can view this now as you collect data according to what's called an observational policy. So that is, every unit receives treatment with what's called the propensity score. This is called pi of x, which is just the probability of receiving treatment given x. And you could imagine now what I went out and did was I collected data according to this observational policy. And what I want is to know, under my interventional policy where everyone receives treatment, what is the outcome? Everyone okay? So I collect data with some biased sampling, and then I want to know if I unbiasedly gave everyone treatment, what would happen? And this would suggest what is known in reinforcement learning and everywhere else. It's the Horvitz-Thompson estimator, or the IPW, inverse propensity weighting estimator. It would say, if you once see this connection, a different way of estimating the average treatment effect is to try to estimate pi, this propensity score, and then reweight everything by the probability of receiving treatment or of receiving control. And once you do that, you will come up with the second natural plug-in estimator, which is this quantity, which is just taking every unit and dividing it by this propensity score quantity in order to debias your estimate. Is everyone okay so far? Okay, great. This maybe also makes clear that somewhere in the middle of the identification, you actually need this assumption that you have what is called overlap, which is that every unit has some chance of receiving treatment or not. When you stare at this form, it's a little bit more clear that something like that should be necessary. Okay.
Why does that apply?
It's just one of those conditional expectations will be badly defined, that's all. Yeah, so somehow to say that this thing is the same as this thing, you need the probability of, otherwise you're conditioning on something that has measure zero, basically. Yeah.
Another question is, should I think about y as continuous or binary in general?
Doesn't matter. Think of A as binary.
So if y is continuous, then this is a very naive question, but we're using independence in order to kind of assert equality of conditional means. Yeah. So maybe if you tell me some more about the distribution, if I make some more assumptions, then I could maybe relax the assumption of independence in some way. Like conditional independence we're using to imply equality of conditional means, right?
Yeah, so you could just directly make the second assumption, which is just independence of the conditional means, but it would just be a weird one to think about. But yes, you don't need the full strength of this independence assumption to go from here to there. Yeah?
Practically speaking, how do you have like two regression models that one model is the with treatment, one without?
Yeah, so you should imagine I'm collecting observational data. There's some fraction of people who took the treatment just on their own. On them, I will fit one regression function. And then there's some other fraction of the data that didn't take it. On them, I'll fit a different regression function.
The same X, but same inputs, but just two regression models.
That is correct. So the regression is helping me extrapolate in some way. But to solve the regression, the input to the regression problems are just the units who take treatment go into one black box that spits out mu0. And then the inputs who didn't take the treatment go into the other black box. It spits out a mu1. And then the regression black box is going to make a prediction at new points. So I'm using regression in some sense to impute what happens in other places. I will answer it again offline. But good. Other questions? OK. OK, so what's the summary so far? Functional estimation problems are everywhere. And maybe one thing that I didn't emphasize enough is that you should think of causal functionals as somehow being more interesting and complex than density functionals. There are more nuisances floating around. There are these regression functions and propensity scores floating around. And so they have a little bit more structure to them. And maybe the main question for the rest of the talk is how do we construct good or optimal functional estimates? Okay. So the first idea, and this goes back to Stein and really Peter Bickel, who's here at Berkeley. And it's the idea of one-step corrections. It's something that Poling told you a little bit about yesterday. So here's the idea that you should keep in mind. So suppose you're trying to estimate a functional. It looks like the integral of phi of p of x dx. So you can think of phi as p log p or phi as p squared. Then these are the kind of density functionals that we were looking at before. OK? So now you can do something. If phi is nice, you can do a Taylor expansion. So you can say the integral of phi of p of x can be written as the integral of phi of p hat plus some sort of first-order Taylor expansion, which is just phi prime. So take some derivative of p hat times p minus p hat plus some quadratic remainder term. Everyone OK so far? I'm just Taylor expanding phi. I'm assuming it's smooth and nice. And so this is something that one can do. So the idea of one-step corrections, so the first term here is the plug-in estimator. It's just construct p hat and plug it into the formula. And the idea of one-step corrections is I can try to estimate this term. This term is very simple. It's just the expected value of something. So the integral of phi prime times p hat is just something you know. And the other quantity is just the expected value of phi prime. Right? So the first order correction is very nice and simple. It's the expected value of something. It's extremely easy to estimate. OK, so this suggests, in general, the following simple estimator. You take your plug-in estimator, you subtract off the term you know, and then you add to it an estimate of this term phi prime times p. Everyone OK? OK, what does this bias? The first thing, the way you should think about this estimator is suppose I constructed p hat on a different sample, and then on a separate half of the sample, I adjusted it by computing this quantity here. Right? So then you can see, OK, this is just an average of some fixed function. And the conditional bias, so imagine I conditioned on the first half of the sample, it would just be driven by the second order term. So it looks like p hat minus p squared. And the variance is just 1 over n. It's just an average. So somehow magically, I've taken a plugin which maybe arguably had some bias like p hat minus p. And I've done this one-step correction. It works somehow out of the box. There's no more assumptions being snuck in, or not too many more. And then you get bias which squares the bias of the plugin estimator. Is everyone OK with this? Stop me if anything isn't clear. OK. So all I'm doing is doing some Taylor expansion, estimating the first order term. Yeah.
How do you estimate p hat using like some empirical density? Then the second term should cancel with the third term.
You should think of it, p hat as like a smooth estimate of the density.
Why is the second derivative there at the intermediate value not important to consider?
You should think of it as I'm going to make enough assumptions that the function is twice differentiable, the functional. So,
but I guess why is that not an important sort of scale to also add to your bias there? Because that could also get very large potentially.
I'm just going to make the assumption that the second derivative is uniformly bounded, say. So it's just some constant. It'll appear if you want to be very careful, but think of it as the integral of p squared, then the second derivative is just a constant.
I guess maybe like a related question is like you can keep going, right? Like I mean, you don't have to just stop at first order Taylor.
So
if
what
drop the bias to like p minus like whatever. Like
sure, but that would require you to estimate this term, and I'm claiming that this requires some assumptions. This is the integral of something times p squared, which itself is a functional. It is not linear anymore, and so it's not trivial to do this.
I guess basically you picked an intermediate value so that you could write this inequality and without it.
Right. I was just curious, yeah, if that could blow up too. Okay.
Great. So maybe you should think of, okay, you often this idea is combined with two things, which is called sample splitting and cross-fitting. So sample splitting just means you estimate p hat on one half, you plug it into this formula and get an estimate of the functional on the second half, then you swap the roles of both of these things, and then you average your estimate. Turns out that if you cared about things like statistical efficiency, which is you cared about getting the right constant in front of the variance, this will often restore that in some settings. Right? So this is
How do they compare to the estimators people propose with that have like moment matching kind of like as I was able to maybe estimate like up to kth moments, like I could approximate the function and using k polynomial k, and then that would also give like plugins now with the moments instead of that. So people do this moment matching estimators, right? Like so.
You maybe hold on to it till the end, because somewhere at the end I will tell you something about that. But you should think of it as somehow here I'm making some very strong smoothness assumptions so that this would be right, and then it'll not make sense to estimate too many more terms. But in the discrete setting, for example, it makes sense to estimate a lot of terms, and then you will do what you just said.
So related to this, the constants and efficiency, we can really get the same thing, or I mean, what I'm trying to figure out, is there a cost here because now you're dependent on the smoothness of the derivative as opposed to just the smoothness of the itself? Like, is it really just?
No, so it'll turn out that the efficiency bound itself depends on what's called the influence function, which is in this exact term, the variance of this term is the efficiency bound. So this was what Charles Stein did, which was he kind of showed that the best you could hope for depends in some way on the derivative, and it depends on this kind of quantity. So that you should think of the only reason I lost efficiency was because of sample splitting, and you might be able to regain it in some cases. Say what?
Yeah, that I'm not, the factor of 2 there, I'm not worried about.
Okay, yeah. So you do not lose. Yeah, you should intuitively imagine that how well you can estimate the functional depends on its smoothness, and so it turns out that whatever the variance of the linear term is the efficiency bound. Okay, great. Okay, so for the average treatment effect, you can go through the same thing. It'll turn out that there it's not a simple Taylor expansion. You have to do something slightly more complicated, and this is exactly what Poling explained, which is you have to compute what is called the influence function of that functional. So you have to compute some sort of functional derivative, and then it'll turn out that whatever, as long as the functional is nice, called pathwise differentiable, then the same logic will apply. The thing that you correct will not be the derivative of phi, it'll be something else, which is the derivative of the functional itself. And when you do this for the average treatment effect, which is a pathwise differentiable functional, you will get something very similar. You will get a plug-in estimator. You can either view it as the Horvitz-Thompson plug-in estimator or the usual plug-in estimator plus some adjustment term. And this adjustment term will be the average of some stuff. Just like in the density functional, the same story will apply to the average treatment effect. The first order correction will just be plug-in plus some stuff. And this correction will involve both the propensity score and the regression functions. So the plug-in estimators involve either one of those two things, and the first order estimator will involve both of them. And this estimator will have, you can analyze it just like we did before. It'll have conditional bias, which looks like a product of the error of the propensity score and the larger of the two, say, regression functions. This phenomenon is called double robustness. So before, when we were doing density estimation, we just got a bias that squared the bias of estimating the nuisance. Here, it doesn't square the bias. It gives you a product of two different biases. Right? So it gives you a product of two different errors. And this phenomenon is called double robustness. It comes up in reinforcement learning and everywhere else. What is interesting about this, and this again goes back to Jamie, is that in order to, the one-step correction can be consistent when you don't have to consistently estimate both the regression function and the propensity score. If you get one of them correct, then you can still get consistent estimates of the functional. And this is kind of a nice property to have. Everyone okay so far?
You kind of said this, but I want to check. The way that we would get this is by pursuing a first-order Taylor expansion. But that is more complicated than what you wrote down because
you have to do what Poling wrote down, which is compute the influence function of the functional. But yes.
Because it doesn't have this form for this problem. Okay. And this is, so was this somewhat is this the canonical way to see this estimator?
Yes. This is how Jamie derived it, if you want. Yes.
This is just a naive question. It, I've heard other people like call this something else. Like Victor calls it double machine learning or something.
I'll tell you what that is in a second. But
Also sees from the inference function perspective.
yeah, so he derived it slightly differently, but it's the same thing. Yeah. I'm looking at Avi if he has an opinion about what we should call this, but all right. So you get some conditional variance of 1 over n just by the same analysis as before. And Ryan guessed what I was going to say next, which is, okay, so this idea is much more general. You can sort of apply it to many different functionals, this recipe of estimate the nuisance on one half, compute a one-step corrected estimator on the second half, swap and average. So you can do this for lots of different functionals. And this, if you're from MIT, you would call this double machine learning. So what they are trying to get at is, okay, you can use a machine learning black box to estimate the nuisance functions, and then your estimate of the functional gets some accuracy which only depends on how well you estimated the nuisance function. So you don't need to know much about the structure of your nuisance function. As long as you are promised that some neural network can estimate it well, you inherit somehow. If you estimated the nuisance well, you plug it into the one-step formula and you inherit some nice properties. Is everyone okay so far? You look very confused.
I'm just confused. Maybe I don't know this area. What are the nuisance in the general functional case?
You should think of your functional depends on some nuisances. Whatever they are, you try to estimate them. They typically involve solving some prediction problem. So solve a regression problem or propensity score estimation problem. You hand those off to a random forest or a deep neural network. They give you back some estimate. You plug it into that formula, which is whatever the one-step correction is, and then you get some bound that looks like this. I'm not being particularly specific. For the ATE, eta would be some combination of the propensity score and regression function. Okay. All right, so maybe importantly, this bound is agnostic, and we'll revisit this fact many times, which is that it doesn't depend on structure on eta, which is I'm not assuming eta is smooth. What I am assuming is that there's some black box that can give me a reasonable estimate of eta. Okay, so are these estimates optimal? And the answer will be somewhat familiar to people in TCS. The answer is no. And the reason somehow has something to do with what's called the birthday paradox. So let me try to explain very quickly why these estimators can be suboptimal. So you should imagine I sample a bunch of people uniformly on the cube, say. Then just by chance, I will get pairs of treated and untreated people who are very, very close by, much closer than you would expect based on, much closer than, say, the average distance between them. So you would see collisions. So if you think of the average spacing between samples as being something like n to the minus 1 over d, then just by chance, you will see things that are quadratically closer. You will see pairs that are n to the minus 2 over d close. And you can try to exploit this fact in order to construct estimates of the average treatment effect or of other functionals. Right? So just by chance, you will see pairs of treated and controlled samples that are much closer than their expected distance. In TCS, you would call this a collision. And these can give you some very low bias estimates of the ATE. So if you're in a smoothness model, so if you think of your propensity score and regression as being smooth, if you somehow cleverly used only these samples that are very close by, you would get very low bias estimates. And maybe you can use this in some way. Everyone roughly okay? I'll give you more details about how this works. So rough intuition, okay?
Like what people do, like they match the match.
Matching is the global version of this. You say, take every person, match him to his closest one. This is like a version of matching where I say, I'm going to only use matches that are very, very close, and I will lose something in variance, but I'll gain something in bias, and maybe it'll work out for me.
This might introduce biases on its own because there might be denser regions that are going to be magnified under this approach, right?
Correct. So you have to account for, especially the covariate density is not uniform, then maybe you're getting collisions because the covariate density is high, and maybe that's not exactly how it works in the functional, and then you have to correct for it. But this may be the basic intuition. What you're saying is correct. So unless something nice worked out, it need not be the case that I can just average things that are close by. It could be very biased for the thing I want. Very good. Okay. So, and again, this story is also quite old. It goes back to Peter Bickel and Yakov Ritov, Birger and Massard, Jamie Robbins. They all sort of highlighted this fact that if you're trying to estimate a density functional and say your density is Holder smooth, then you can dramatically improve the plug-in estimator. You can also dramatically improve these first-order corrections. There's a similar story for causal functionals in some cases, and I'll tell you what it is. And in all of these cases, the minimax optimal estimator, the optimal thing to do is to use what's called a higher-order U statistic. In TCS, this would be called a collisions-based statistic. And you can think of this roughly as trying to estimate the second-order term in the Taylor expansion, which is maybe what Andre was saying. But you should keep in mind that constructing such estimators require you to understand very carefully how bias and variance work in your model, because you're going to very aggressively try to reduce the bias, and this might inflate the variance, and you need to know how to trade those off. Okay, so again, this is just a high-level thing. So let me give you a concrete estimator, just so you have something in mind, and you see what the complications are. So think about estimating the integral of p squared, and say p is s Holder smooth. That means it's just s times differentiable, say. It turns out that a minimax optimal estimator of this functional is exactly the thing I wrote here. You should think of it as, it looks like a kernel density estimate, but it's really just counting how many pairs xi and xj are within hn of each other, and then normalizing it in the right way. Okay, so this is really just counting how many pairs are very close by. This will give you an estimate of this functional. What is crucial about all of this is that now you need to take the bandwidth in a certain way, and this bandwidth choice will be far more aggressive than the usual smoothing kernel bandwidth. So that is, it will be, in many cases, much smaller than n⁻⁻⁴d. And in particular, you should think of it as you're going to do this thing like something like a kernel density estimate with a bandwidth where most of the bins are empty. And this would be a strange choice if you were trying to estimate the density, but it would be a not so strange choice if you're trying to estimate the functional. And again, you should keep in mind this involves some careful undersmoothing. You're choosing a bandwidth that's often much smaller than n⁻⁻⁴d. And you should think of this as doing something. It'll blow up the variance. So if you thought of this as somehow underneath there's a density estimate, that density estimate would be very bad. It would have much larger variance than bias. But if you think about it, the functional itself involves another layer of averaging. It's kind of like saying, what is the expected value of p? So there's another layer of averaging that's going on, and that averaging brings the variance back down. Is everyone okay with this? Okay. So let me tell you the story via a list of rates. If you're not used to looking at non-parametric rates, just ignore everything I'm about to say. So you should think of it as the estimation rate, if I looked at it on some squared scale, would look like n⁻²s over 2s plus d. If you use the plug-in estimator, and I messed up, you would square that rate. It would look like n⁻⁴s over 2s plus d. And, oh, no, sorry, the plugin, correct, sorry. The plugin just inherits the estimation rate. The first order rate would square it. So it would look like n⁻⁴s over 2s plus d. And the minimax optimal rate turns out to just double everything. So that is, it looks like n⁻8s over 4s plus d. It turns out that that's the best you can hope for. It's much, much, much faster than the plug-in rate and the first order rate. And
What is S?
S is the number of derivatives that are bounded, say. So if you think of Lipschitz, then S is 1, but otherwise it can be some number. So maybe the important thing, and this is sort of the answer to Stein's original question, was that, for instance, if you think about the minimax optimal estimator, when S is bigger than d over 4, so you have some reasonable amount of smoothness, you actually back out to parametric rates. The problem is as hard as estimating a single number, but if you don't have enough smoothness, you get some non-parametric rate. And so this was what he was after. He was kind of trying to understand when do you get parametric rates and when not. Is everyone okay so far? What is the? Is that why there are?
Oh no, I just think that like if you had like PQ or something, instead just like.
Yeah, so it turns out that the integral of p cubed, for example, you would get the exact same rate. Everything would be the same. And it comes from this fact that you are going to go about doing Taylor expansions and estimating quadratic-ish terms. And then if you're clever, You should think of this as the rate for essentially any smooth functional, as long as you can carry out this program. Okay, so
this comparison in grades are tight because you just gave up the bound.
yeah, so I mean, it's not tight in the sense that you have to define these classes of estimators, and then maybe you could argue about lower bounds. But otherwise, everything except the minimax rate, there's no lower bound. I don't know what it means to say lower bound for a plug-in estimator. You would have to define what plug-in estimators are, and that can be a bit controversial. So,
But we know some situations where this is essentially the rates for.
yeah, if you agreed with me that a plug-in estimator is you take an optimal estimate of the density and plug it into some formula, then you can correspondingly give lower bounds for those particular estimators. But people would argue with this because you can undersmooth a plugin, you can do all sorts of things, and then maybe you would land somewhere else.
I missed, is the T the square root of the density here for all of them?
You should think of the story as roughly being true for any smooth functional. So any integral of phi of density for sufficiently smooth phi, this would be the story. Yeah.
So that's actually, you just said something that's very interesting. What if you undersmooth the plugin?
You can do this. In practice, it might be arguable about how exactly do you do it. And so this is why practitioners prefer, rather than trying to undersmooth the plugin to get here, you prefer using the first order rate because it's using an optimally tuned thing, which you know how to optimally tune, and then maybe. But the story is much more complicated. If you undersmooth the plugin, sometimes you will get optimal rates and sometimes not.
Is S part of the algorithm? Or
Is S known to the algorithm, you mean? Yes.
If I get it wrong, what happens?
Yes. The answer is the same as what happens in regression. You could, if you suboptimally pick bandwidths, you will get some suboptimal rate at the end. And you can say quantifiably how suboptimal. But yeah.
Are there any other estimators other than the use cases to achieve the new ones?
I'm not sure I know the answer to that question. Do you have a candidate in mind?
I don't know.
I don't know the answer. Probably, but I don't know one. The ones that I know all involve this way of doing it. Okay, good. So let me keep going because I'm going to run out of time pretty quickly. So let me tell you the ATE story. The ATE story is somehow similar. It just says, okay, if your mu1 and mu0 are alpha holder, your propensity score is beta holder, then under some set of somewhat heroic assumptions, you might hope that the rate looks like what I said. The optimal estimate of the ATE has a rate that looks like n to the minus 8s over 4s plus t. And what is interesting about the ATE is that the correct smoothness parameter will be somehow an average of the smoothness of the propensity score and the regression function. This is somehow a reflection of this double robustness property. That is, even if one of them is not smooth, as long as the other one is smooth, you still have some hope of being able to estimate this functional. And maybe the highest level takeaway is just estimating smooth functionals is often polynomially much easier than estimating the underlying nuisance functions. Okay, good. I'm going to speed up. I will try to keep taking questions, though. So what is the trade-off that we've seen? We will revisit this again. You should think about the first-order estimator as having this agnostic error bound. It's compatible with this double machine learning idea. Its error bound just depends on how well the black boxes estimate various nuisance functions. It's a very simple and robust correction to the plug-in estimator, but it's not necessarily minimax optimal over smoothness classes. These higher order U statistics are a bit more cleverly designed. They exploit the collisions or these holder assumptions very carefully, and they're minimax optimal. And you can ask various questions. So one of them is how specific is everything that we did to density functionals or to the ATE? The other is there this somehow seems like there's some trade-off. I've given up something in order to gain minimax optimality, and you can ask, is it necessary? And the last question that you might care about is, okay, what happens outside smoothness classes? And so, for instance, Ramya was maybe asking if you did it over a categorical thing, of a multinomial, so you have no smoothness assumption, everything is discrete, then what can you say about these problems? Right, so all of these are interesting, and so I will try to give you a little story about each of them. Questions so far? Good. Okay, so maybe I'll skip the preview. and tell you a little bit about a slightly different functional, ostensibly not a functional itself, but it'll turn out to be one, and it's kind of an interesting one. So this is called the conditional average treatment effect. So the ATE, as I said, is a popular target. It measures what's the average effect over a population. This is saying what's the average effect if everyone was treated versus no one. It can obscure somehow heterogeneity. Maybe the treatment helps some fraction of you and hurts some fraction of you, and I'd like to understand this better. So the effect, for instance, could be 0 on average, but it could be benefiting a bunch of people quite a lot and hurting a bunch of people. And I would like to understand this heterogeneity. And this, of course, will inform, if you understand this, if you're able to estimate somehow personalized effects for each individual or each individual set of covariates, then you could better inform policy decisions, you could optimize treatment allocations, you could do all sorts of things if you can understand this heterogeneity. And formally for us, what do we want to understand? We want to understand this quantity. It's called the conditional average treatment effect, or the heterogeneous treatment effect, or the personalized effect. You should think of it as it's just the difference of these two regression functions, not averaged over the whole population, but at, say, some fixed point x0. Okay, good. Now, if I pose it this way, it's not obvious that this is at all an interesting integral functional. It's really like a difference of two regression functions at a point. If I just said estimate a regression function at a point, that's not an interesting functional. There's no additional averaging going on. So the best you can do for estimating a regression function at a point is just to use a plug-in estimator. That is, use the estimate of the nuisance at that point. It'll turn out that it actually is one, but it's not obvious why, maybe, yet. Okay, so the simplest idea that you could use to estimate this heterogeneous effect is to use the plug-in estimator. And when can this be suboptimal? So the case when it can be suboptimal is if these two are maybe not smooth, but their difference is very smooth. Right? This is when it'll start to behave like an interesting functional. So this is maybe the canonical case you should keep in mind. Mu1 and mu0 are maybe not so smooth, but their difference tau is actually quite smooth. And maybe this is somehow a natural setting to think about. You should think about mu1 and mu0 as modeling some outcome process. It could be quite complicated. But if, say, my drug has no effect whatsoever, the difference is 0. Right? So maybe the distribution of headaches amongst a population is kind of complicated, depends on a lot of features. But maybe my aspirin or whatever just has no effect whatsoever. And then tau is very simple. But mu1 and mu0 are potentially quite complicated. Everyone okay so far? Okay, so it's under this assumption that this will become an interesting problem. So here's the picture you should have in mind. Maybe mu1 and mu0 both are identical. They look kind of wiggly. You sample some data, you try to estimate mu1 and mu0, you'll construct some estimate, and then when you take the difference, you'll get some very wiggly thing. You're not somehow correctly exploiting the fact that their difference is smooth, even though they're individually not very smooth. Okay. Let me sort of... Okay, so I'll tell you the story quickly. There are lots of estimators here that have come out of Stanford and Berkeley and various other places. So particularly Stefan Wager, Susan Atty, Hito Imbens, Soren, Jas Sekon, Bin Yu, Peter Bickel. They've all written papers which all proposed estimators of what are called heterogeneous effects. These are essentially localized versions of these one-step corrections or localized versions of different estimators of the ATE. And they have fancy names. They're called the R learner, the X learner, the T learner. They have all sorts of names. And again, it's a little bit unclear if any of them achieve the right rate. And it's also unclear what the right rate is and when it's achievable. So let me tell you just a result, and then we'll move on quickly. So one thing that you can try to do is to try to instead localize a higher order estimator, so one of these collisions estimator, and then something interesting will happen, which is suppose that your propensity score is alpha smooth, your regression function is beta smooth, your conditional average treatment effect, your heterogeneous effect is gamma smooth. So you should think of gamma as somehow being large. Then you will get a rate, the minimax rate, by localizing a higher order estimator of the ATE. And the minimax rate is kind of interesting. It'll mix for you an estimation rate for tau with a functional estimation rate for the nuisances. And it puts all of these together in some way. And the way you should think about it is, again, if you have enough smoothness in the nuisance functions, you can estimate as though you observe both of the potential outcomes. This is sort of the best case scenario. And otherwise, you will get some slightly slower rate that will depend on how well you estimate the nuisances. But you get some interesting hybrid rate that mixes a functional estimation rate with a function estimation rate. I will not go into much detail here, but if you have questions, you can stop me. Okay, I will skip it. So maybe the high-level takeaway here is just that in contrast to density functionals, causal functionals, because they have this interesting structure, they can have interesting local counterparts. That is, the heterogeneous effect has no natural counterpart in the density model. It's no natural interesting counterpart. And so it's all due to the fact that these causal functionals have this thing that combines regression functions and propensity scores in some way. The optimal estimator of this personalized ATE is some localized higher order estimator. It inherits both of its strengths and weaknesses. It's minimax optimal in a smoothness model, but it's not agnostic, unlike all of the previous work that proposed localizing the average treatment effect. Localizing first order estimators, those have this double machine learning flavor of error bounds, and the minimax optimal estimator doesn't. And so now we'll just revisit this question of whether it's necessary or not. Yeah, so you should think of the conditional average treatment effect as the average treatment effect of individuals around some point. So I could just take some value x naught, take some people that are close by and estimate the ATE there. That would be a localized version of the ATE, and it'll give me a reasonable estimate of the Kate. It's not necessarily what people do, but that's what I mean. Okay, so let's go back to this question of, is this trade-off necessary or not? So to remind you, these double machine learning estimators have this nice property that their error bounds are agnostic, and no other structural assumptions were used in analyzing them. And so this maybe begs a question, which is, if you're willing to only assume access to some black box that returns reasonably accurate nuisance estimates, how well can you estimate a functional after that? And okay, so one needs to formulate this question, and I'll do so in a couple of cases. So here's the natural minimax formalization of that question. Suppose that I give you a pilot estimate p hat. It's constructed on a separate sample, and you want to estimate some functional T of p. So you could imagine defining the following model class. What I'm going to guarantee you is that your pilot estimate is accurate. You don't know its accuracy. It has some Rn accuracy. But beyond that, I'm not going to give you any other assumptions. And so you want to estimate something like the integral of p squared. And the only assumption I'm willing to give you is that I'm going to hand you a pilot estimator, and it's reasonably accurate. Okay? And now I can define a minimax rate as saying, OK, how well can I estimate inside this model family? So if I give you samples from a density, the only guarantee is that it's somehow the pilot estimate that I handed you is somehow accurate. That's the only guarantee I'm giving you. Now, how well can you estimate a functional? And this you should think of as somehow asking, what's the fundamental limit of this double machine learning point of view, where I'm going to outsource to a black box an estimate of the nuisance, and then I want to construct downstream an estimate of a causal effect. OK, so what is the guarantee that one can give? Well, the plugin, the first order estimator, which we described before, will give you these agnostic error bounds. It will square the error of the nuisance estimate, and you'll get some variance which looks like 1 over n. Right? So this is the analysis that we roughly did before. This is the first order Taylor expansion analysis. And the result that we showed in some paper is basically that this is also tight. That is, this is the best you could hope for in the structure agnostic model. So if all you're willing to assume is this, there's no Holder smoothness, there's nothing else going on, this is the only assumption you're willing to make, then the minimax rate is exactly what is achieved by the first order estimator. And the way you should think about this is that these higher order collisions-based estimators are only going to give you improvements when you have some sort of Holder structure that allows you to exploit undersmoothing in the right way. And if you're not in that world, then you should think of the first order estimators as essentially optimal. OK. Questions about this?
That can be well approximated by that black box.
I'm going to say the black box gives you an estimate constructed on a separate sample, and all I'm going to give you is that the true sampling density is within some Rn of that.
The quantifier for t is like for any t which is differentiable. This is true, or?
Here I'm talking about the integral of the density squared. In a second, I'll tell you what the result is for. Yeah. Oh, thank you.
It's clear, yeah.
Say what? Here, you should think of it as L2 for the integral of p squared. There's some story about what the right metric is, but I won't get into it. But think of it as L2 here. Okay, very good. So something similar happens for the AD. You can ask the same question. I give you pilot estimates of the regression functions and the nuisance, and all I'm willing to tell you is that the regression functions are Rn accurate and the propensity score is Sn accurate. This is what I'm willing to give you. I'm not giving you any additional assumptions, and the question is how well can you estimate the average treatment effect? And now this is a result due to G.K. Jin and Vasilis Serkanis. It basically says that in this structure agnostic model, the first order estimator of the average treatment effect is minimax optimal. So that is, the first order estimator has this double robustness property. It has a variance that looks like 1 over n, and whatever additional term which looks like the product of the mean squared errors. And that's the best you can do. So the first order estimator of the average treatment effect is in fact optimal if all you're willing to assume is that your pilot estimators are accurate in some sense. Okay, and the takeaways are exactly the same as before. You should think of it as any additional improvements that you can get over this first order estimator come necessarily at the expense of imposing more assumptions on the problem. Questions so far?
Yeah. It's true for some range of Rn and Sn that keep this bounded away from the minimax optimal rates that you mentioned for the higher order smoothness classes, or is this showing go down to that level?
Well, yeah, so there's some point at which if Rn and Sn are essentially 0, you can actually improve on this a little bit. So there's some point at which the plugin becomes optimal. And it's a little bit complicated to describe, but you should think of it as outside that, this will, it'll never contradict the minimax rate that you said before, that over smoothness classes.
I was asking something slightly different, which is that when I'm in the regime where the holder smooth rate is not 1 over n, because I haven't hit the elbow or whatever, but it's faster than the agnostic rate, does this accommodate that regime? If I had assumed that I had an estimator that had a good enough mean squared error.
So in the holder case, the thing that's driving the improvement is not that you are improving the estimate of the plugin. It's something else that. So let me answer this offline, because so what is, you will never go below this floor, even in the holder problem. You will improve Rn and Sn to some amount, but it's never the case that the structure agnostically, you should not be able to improve this. The improvement that is coming, that is the holder rate is faster, but that is coming somehow non-structure agnostically. So you're going to use densities that exploit, I mean, everything, you will exploit properties of the problem that are more than just what I've given you here. Does that make sense? Let me, I'll answer it again offline, yeah.
Can anything be said about the constant on the 1 over n, like in a structure agnostic local minimax something? I don't know.
I don't know the answer. I've wondered this. I don't know exactly. But okay, so.
I'm still a bit perplexed by your, what you write as script. So maybe go back.
This?
Go back to the
Yeah.
for instance.
The one before.
Yeah. Yeah.
Okay. Good. Yeah, you should think of it as, yeah, the model itself depends on p hat. So you should think of it as, it kind of only makes sense if you think of p hat as constructed on a separate sample and handed to you. And then cal p is like a random model in some way. And the minimax rate doesn't take an expectation over p hat in any sense.
So then when you talk about optimality, for instance, of this one-step estimator, does that depend on any properties of p hat?
No. So that yes, and that's what I was saying, that they give you these agnostic error bounds, which means they give you an valid upper bound in this setting, and then you can give a lower bound in this setting. But the upper bound doesn't depend on any property of p hat or any particular strong property of p hat. And in 5 minutes, let me tell you the last story. So this is the The other case that you can consider is this case when covariates are discrete. So here, again, you have no smoothness at play. So this is the setting that people in TCS care about most or analyze most, which is that you think about the case when X is categorical. So that means you just have a multinomial sample. So X has a multinomial distribution. And what is going to make this problem hard is that the number of categories can be potentially large. And this is a way of trying to understand, again, what can I do with causal effect estimation when I don't assume any smoothness? OK, the setting is exactly the same. I want to estimate, say, the ATE as before. And this connects to a line of work which maybe started with Liam Paninsky a while ago and then was revived and given new energy by Greg and Paul Valiant, and then Jiantao Jiao, who's here, Karthik Venkat, Yanjun Han, Saki Weissman, Yihong Wu, and Pengkun Yang. They all sort of wrote all these papers about estimating the entropy in this setting. And so I'll tell you a little bit about what they did and then what happens in causal effect estimation. OK, so what is the setting that they were interested in? They're interested in estimating the entropy. And it's a density functional over a categorical domain. And here's the result that they showed. Essentially, the minimax rate, it looks like you should think of it as d over n times log d squared. You can ignore the second term. And what is this saying? It's saying that, OK, the plug-in estimator would get this rate without the log factor in the denominator. And so what it's saying is that you can improve on the plug-in estimator by this additional log factor. And essentially, that's the best you could hope for. OK, so initially, maybe this result itself is kind of surprising. It says you can estimate the entropy of a categorical distribution without even seeing a sample from every category. So most categories you haven't even seen once, but you can estimate the entropy reasonably accurately. If you haven't seen this before, this should be kind of surprising. It somewhat fits our theme. Estimating a functional of the distribution should be easier maybe than estimating the distribution itself. And you should think of d over n as the correct rate for estimating the distribution, and d over n times log d is somehow the right rate for estimating the functional. Everyone OK? To maybe relate it to what you saw before, you should think of this as saying somehow you can improve on the plugin by this one logarithmic factor. It's somewhat modest compared to the smooth case. In the smooth case, all these Taylor expansion tricks work, and you can get much more significant polynomial improvements. Whereas here, in this case, there's no smoothness. The functional you're estimating is necessarily kind of badly behaved. And so you cannot get significant improvements. Is everyone OK so far? And so the way to think about it is something like the entropy. It has this function p log p in it. When p is close to 0, which is the case when you're in a distribution with many categories, then this p log p function can behave somewhat erratically. So what you will have to do is try to approximate it by some polynomial, and then you'll pay some price for doing this. Everyone OK so far? Good. OK, so I was going to explain to you how polynomial approximations come up, but I will skip it. It's kind of neat. But let me tell you what happens with the ATE. So something very similar happens. The ATE, maybe you should think of as also a functional, and I will explain how in 1 second. So maybe here's a useful place to start. So you should think of when you're trying to estimate the ATE, let's say first I want to only focus on estimating the effect on the treated units. Then you should think about, after some Poissonization, this is the model. In each category, I observe a draw from a Poisson with n times p. That's the covariate density. Then I observe a draw from n times the propensity score times the covariate density, and another one from n times the propensity score times the covariate density times the regression. So the thing I'm interested in estimating, I give you these three x, a, and y, and the thing I'm interested in estimating is p times mu. And you should think of it roughly as the product of these two divided by this. So if you think about it as a polynomial, it looks like xy divided by z. That's the nonlinear function that I want to estimate. And again, it's a thing that can be badly behaved. And so the same thing happens. You can do some analysis and kind of relate it to these ideas that came up in entropy estimation, and then you will prove the following thing. At least the lower bound says that in this categorical model, the best you can hope for is this log d improvement. And so you should think of ATE estimation in the discrete case as being essentially as hard as entropy estimation. There's no essentially very little that you can improve over a plug-in estimator in this context. OK, so let me stop here. And so Okay, sorry, let me just say that there are many people in Berkeley who work on causal inference. There's lots of chances to learn. Avi is here. Many people in the stats department, public policy, everywhere else. And so, and there's lots of chances for theorists to contribute. It's an area with lots of exciting connections to things that all of you know a lot about. Thank you.
Questions for Siva?
Please say like what basic or from different topics?
So do you mean in the case of entropy? Yeah, so I guess the answer is you're going to approximate it by a log d degree polynomial. And then when I give you, say, whatever, d over log d samples, there'll already be some categories where you will see log d many samples. And on those categories, you can get a good estimate of the entropy. So what's going to happen is, again, you're exploiting collisions, but you need much higher number of collisions to be able to get a good functional estimate. Does that make sense? So you don't need to see every category. As long as you see a few categories sufficiently many times, you can get a reasonable estimate, say, of the entropy.
Okay. All right. Let's thank Siva again.
Thank you.